In this video, we're going to talk about forces. Generally speaking, force can be defined as that which changes or tends to change the state of rest or uniform motion of a body. The description of a force's magnitude without also specifying its direction has little practical value. And since force has a magnitude and a direction, therefore force is a vector. And often there are a number of forces working on an object. Well, the resultant force would be the single force that would produce exactly the same effect as all of the forces acting together. Usually when we add vectors as forces, the resultant is, the sum of all the forces. Equilibrium, on the other hand, is a state in which an object does not move. So the equilibrant of a number of forces would be the single force that would oppose the resultant of the forces and therefore create zero motion. So therefore, when the equilibrant is applied to the object is in a state of equilibrium, and the equilibrant is therefore equal to the resultant times -1. So imagine two or three forces acting on an object, creating a resultant. If we introduce the equilibrant, it exactly cancels out that resultant, and we're back to a state of equilibrium. And at the bottom of the screen, it reminds us that the Newton is the unit of measurement for force, and 1 Newton is equal to the amount of force necessary to cause a mass of 1 kilogram to accelerate at 1 meter per second squared. So in other words, 1 Newton equals 1 kilogram meter per second squared. So let's do an example. Two children, James and Fred, are pushing on a rock. James pushes with a force of 80 newtons in an easterly direction, and Fred pushes with a force of 60 newtons in the same direction. We'd like to know the resultant and the equilibrant. Well, to determine the resultant's pretty straightforward. We just imagine a 80 newton vector in one direction, and then a 60 newton vector as well. So the resultant is going to be 140 newtons in an easterly direction. So the equilibrant will be the force that perfectly opposes that resultant and would put us back to a state of equilibrium. And so that would be 140 newtons in a westerly direction. And so here is our more formal, neater looking solution. You have 80 newtons and 60 newtons, add to make it 140 newtons. And so therefore the equilibrant will be 140 newtons in a westerly direction, perfectly opposite to the resultant. Now, of course, forces acting on an object are not always collinear. So the manner that we determine the resultant force is to add the vectors representing each of the individual forces. And we use numerous different methods to do this. We talk about the triangle law of addition. There's also something called the parallelogram law of addition, which I don't typically get into much, if at all. I like the triangle law of addition myself. And then there's also adding components. We're going to talk about that more towards the end of this video. So the best way to approach the situation will often depend on the specific question, and it'll be helpful for us to recall the sine law and the cos law. So here's the sine law written in front of you, and here is another version of the sine law. A lot of times we use the first version of the sine law when we're looking for an angle, and we use the second version of the sine law when we're looking for a side. But of course, it doesn't really matter. Just remember, when you're looking at a triangle, if you've got the angles A, B, and C, we typically devote capital letters for the angles, and then the small letters typically will represent sides, and it'll be the side opposite the angle. And so that would look like that. Our cosine law tells us that c squared equals a squared plus b squared minus 2ab cos c. But remember that the angle between two vectors refers to the tail-to-tail angle. But often in our calculations, we move ourselves tip to tail and we're using a different angle. A lot of times it's 180 degrees minus the angle between the vectors themselves when they're tail to tail. Just something to keep in mind. So now imagine we've got two forces of 20 newtons and 40 newtons, but they're acting at an angle of 30 degrees to each other. We want to determine the resultant. So we can imagine the forces like this. It's important to draw them tail to tail first because we're told what the angle is between them, and that implies the angle when they're tail to tail. But to add them, of course, we're going to move them tip to tail in order to be able to add them. So imagine that 20 Newton force just slides over to here, and we can cross that out. And now we're going to have to think about what that angle is. Well, it's going to be 150 degrees because this angle here that I crossed out and this angle are going to need to add to 180 degrees. Okay, so you can see the neat diagram written in the bottom right. Our resultant is the vector that goes from start to finish. And so now we're going to use the cosine law to figure out the length of that third side up there. So when we do that, we see that the magnitude of that resultant will be 20 squared plus 40 squared minus 2 times 20 times 40 times the cos of 150 degrees. And that's roughly equal to 58.19. So we now know the magnitude of the resultant is approximately 58.19 newtons. But we still haven't fully described the force vector itself because we need a direction. So we're going to see if we can figure out the measure of this angle alpha down here. What we do, the reason I'm using that angle is I go back to the tail of the resultant, the part without the arrow, and I want it, if I have it, especially if I have it tail to tail with another vector, that's going to be a good angle for me to reference when I'm describing the direction. I'm not as interested in the angle made at the tip, but this angle made at the tail is the better one because the angle between two vectors is always tail to tail. So that's sort of the more fundamental one. So using the sine law, we can use the sine law without fear of repercussion because we've already determined the largest angle there is 150 degrees. So that's obtuse, so it's clearly the largest angle. So we can use the sine law and with no fear of ambiguity because we're looking for an acute angle. Using that sine law right here, we see that alpha is roughly equal to 9.9 degrees. Okay, so we now have to put the original vectors tail to tail. See, this question didn't talk about any directional aspect. It didn't say north, south, east, west, left, right, clockwise, counterclockwise, up, down, nothing like that. So because of that, it was very general in the way it was worded. So we have to give a general statement in response. And in order to do that, we've got to put the original vectors back tail to tail. So we put them back tail to tail. You see that done right here. And now we're going to try to remember that that was a 30-degree angle initially. If you go back to our original diagram, when we put those two forces tail to tail, that was a 30-degree angle. So we put that 30 degrees there, and now we can see that our alpha, that red angle at the bottom, is 9.9 degrees from the 40 Newton force to the 20 Newton force. If it was rotating away, like if somehow that resultant vector in another question somehow ended up here, I'd say 9.9 degrees rotated from the 40 Newton force away from the 20 Newton force. But that's not the case here. In this particular case, it's rotating back towards it. It's getting closer again. So we word our answer this way. And you might say, well, could I also, instead of saying 9.9 degrees from the 40 Newton to the 20 Newton, could I say 20.1 degrees from the 20 Newton to the 40 Newton? And the answer is yes. Okay, now a group of forces is said to be in equilibrium when there's no movement. So if we have two forces in equilibrium, it's going to look like that. One and another, they're collinear. One's the negative of the other. Pretty straightforward situation. If we have three forces in equilibrium, we're creating a closed triangle. Four forces in equilibrium might look like this. We're creating a closed quadrilateral. And so when there's more than two forces in equilibrium, they're going to form a closed polygon more than likely. So now let's ask ourselves if it's possible for three forces of 2 newtons, 3 newtons, and 4 newtons to be in equilibrium. The short answer is yes. you can make a triangle where one side is 2, one side is 3, and the other side is 4. That's a very possible thing. If that last side, instead of being 4, if that was like a 6 or an 8, we would not be able to make that triangle, but it's a 4, so we can definitely close that triangle off. We have equilibrium. Now, what's it look like when you can't do it? Well, it looks like this. 15 Newton, 18 Newton, and 36 Newton forces cannot be in equilibrium because the sum of 15 and 18 is 33. That's less than 36. So even if I make these two collinear, this third force is going to get me back here, and I'm not closing it off. There's a gap here. I'm not in equilibrium. There is a non-zero net resultant. So it's impossible for those forces to be in equilibrium. Now, let's go back to the previous example. If we had the forces of 2 newtons, 3 newtons, and 4 newtons in equilibrium, let's figure out what the angle would be between the two smallest forces. Now, there's a little bit of a twist ending at the end here that might surprise some of you. So first we'll draw the diagram. We've got 2 newtons, 3 newtons, and 4 newtons. Now we're interested in the angle between the two smallest forces, so we're going to figure out the angle up at the top. That's not exactly what the final answer is going to be, though, as you see. We'll call that theta for now, though. And we're going to just use straightforward cosine law. 4 squared equals 2 squared plus 3 squared minus 2 times 3 times the cos of theta. We go through our steps. Ultimately, theta is roughly 104.5 degrees. So we can put a 104.5 degrees there. But if that's your final answer, it's actually wrong. Because remember, when we say what's the angle between the two smallest forces, whenever we talk about angle between two vectors, between two forces, it's always when they're tail to tail. This is tip to tail. So when we're making that general statement, angle between two forces, we need to reconsider our diagram. So 104.5 degrees is the correct answer to that diagram. But if we put them tail to tail, that alpha is going to be equal to roughly 75.5 degrees. There should actually be a couple of approximately symbols here. Yeah, so that alpha will be roughly equal to 75.5 degrees. And so we can say the angle between the two smallest forces, the 2 Newton and 3 Newton force, is roughly 75.5 degrees. Now, what if we want to resolve a vector into its component vectors? Well, it's often convenient, like it says in the first bullet point, to do this. And second bullet point, in 2 dimensions, this is most commonly done by considering the horizontal and vertical components of a vector. In 3 dimensions, it's most commonly done by considering components along each of the 3 axes. Well, let's focus on the first situation where we're in 2 dimensions. Imagine we've got a vector shown at the right. Now, if we want to break that into a horizontal and vertical component vector, we can do so. That original vector, the diagonal one, could be described, if we wanted, as the component of that horizontal vector and that vertical vector. Sometimes you'll see the horizontal component vector referred to as FH and the vertical component vector as FV. Sometimes you'll see them referred to as FX and FY, like we've done here. Well, this is kind of like a backwards question in a way. A lot of times, up until now, we might have given you a vector that's horizontal and a vector that's vertical and asked you what's that resultant diagonal vector. What's interesting here is we're giving you the resultant diagonal vector, and then we're asking you what would the horizontal and vertical components of that be. What's the advantage to this? The advantage to this is sometimes when we're adding numerous vectors, it can make our life a little easier if we break each one of them up into these horizontal and vertical components. So going back to our original question, it's a straightforward SOHCAHTOA opportunity. We can see here that if you think in terms of SOHCAHTOA, cos theta is going to equal the magnitude of fx over the magnitude of f, opposite over hypotenuse. If you then rearrange this equation, you get that first equation typed out there. And going back to this diagram, we can say that sine theta would be equal to adjacent over hypotenuse. And so that sine theta would be the magnitude of Fy over the magnitude of F. And if we rearrange that, we would get the second typed out vector. So it's sometimes convenient just to have those formulas ready at your fingertips, the two circled equations right there. And so now let's do a question where we begin using these concepts. Imagine Kayla's pulling on a rope attached to her sleigh with a force of 200 newtons, and the rope makes an angle of 20 degrees with the horizontal. We want to know the force that pulls the sleigh forward. That would be the horizontal component, and we want to know the force tending to lift the sleigh. That'll be the vertical component. So we can start with the horizontal ground along the bottom and that 200 Newton force going 20 degrees to the horizontal. There's only one vector there. That horizontal line along the bottom is not a vector. It's the horizontal ground. And so we can think of Fx as being the horizontal component. Fy is the vertical component. Using the formulas we established on the previous page, the magnitude of Fx will be 200 newtons times the cosine of 20 degrees, which is roughly 187.9. And the magnitude of Fy will be that 200 Newton force times the sine of theta, which will ultimately be approximately 68.4 newtons. So force tending to pull the sleigh forward is roughly 187.9 newtons, and force tending to lift the sleigh is approximately 68.4 newtons. Okay, now this is a very interesting question. We have a mass of 20 kilograms suspended from a ceiling by two lengths of rope that make angles of 60 degrees and 45 degrees with the ceiling. We want to determine the magnitude of the tension in each rope. So first we'll draw our diagram. Okay, now right now we have no vectors drawn so far, but what we do have is a rope and a ceiling that make an angle of 60 degrees with each other. And we have that same ceiling and a second rope that make an angle of 45 degrees with each other. So again, no vectors are drawn so far. But what's interesting is this is a situation of equilibrium. There's no net force here because there's no movement. That mass is suspended in the air. It's not moving at all. So there must be some either a couple of collinear forces acting against each other, or perhaps a closed polygon of forces. Well, in this case, there actually will be a closed polygon of forces. And specifically, this is what I mean. We're going to have a force of gravity pulling down, but since nothing's moving, there must be one or more forces acting to oppose that. Well, there are. One of them is tension along the rope, and another one is tension along the other rope. And those three arrows combine to form zero. In other words, if we take them, we take the vertical one that goes straight down, and now we take this one right here that moves up to the left, it'll look like this. And this one right here that moves up to the right, it'll look like this. We're going to close off a triangle. Or conversely, we could start with the vertical and then take the one that goes up to the right, draw it that way, and then take the one that goes up to the left and draw it that way. Either way we think of them, we're going to have a closed triangle of vectors in this question. So let's figure out those magnitudes. Well, one thing that's important to know if you want to go further in this course is that the force due to gravity is going to be 9.81 meters per second squared, roughly, times the mass of the, times whatever the mass of the object is, assuming we're at sea level on planet Earth. So when we do that multiplication, we get 196.2 newtons. And again, that's approximate, but we'll use 196.2 for the rest of the solution. So we've got tension running up each rope. So we draw that 196.2 going down, but now we have tension running up each rope. So we can think of those tension vectors like this, one going up here, one going up here. Okay? And using the Z pattern, we see the following with respect to angles in the diagram. So I'll go back a slide, and what I'm saying is this horizontal ceiling and this imaginary horizontal line are parallel lines. Well, we've got a 60-degree angle here. That means we also have a 60-degree angle here. Now, by the way, this is, like it says, method 1. We're going to do method 2 where we use the components in a bit. But first of all, we'll do it without the components. So this first question, we see that we've got a 60-degree angle created down there. Again, a method 2 is coming. And now we have, again, a horizontal ceiling. And if we look at the right-hand side, we see that this 45-degree angle will replicate itself down here. We've got a couple of 45-degree angles. So that's what we see here. Okay? Now, we're going to move the vectors around to create equilibrium. And this means we're going to have a closed triangle of vectors drawn tip to tail. This is what I was saying a little while ago. So when we do that, we take this 196.2 Newton force right there, and we put it down. Then we take this vector that I've called T2, and we move it tip to tail with the 196.2 vector. And then we take this other one right here that I've called T1, and we move it tip to tail with that, and we close off our triangle. Okay? Now we're going to draw imaginary horizontal lines, and I draw 3 of them. Now, what's the point of that? Well, here's the point of that. We know that T2, the base of it, the tail of it creates a 45-degree angle with the horizontal. So I know this is going to be a 45-degree angle right here. That is going to fall right in there. And I know that the tip of it, see, here's the tip of it, and that tip of it is making a 45-degree angle with a horizontal. So I can put a 45-degree angle up here. Now this T1 right there, that T1 is making a 60-degree angle with a horizontal. So I can put that 60-degree angle with this horizontal line. And then this 60-degree angle here, which is at the tip of it, where the arrow is, that's making a 60-degree angle with a horizontal line, so I can put a 60-degree angle here. Now, when you put that 60-degree angle with the horizontal, the weight due to gravity is straight down, so it's vertical. So this 60-degree angle is inside of a 90-degree angle, making this other piece 30 degrees. And this 45-degree angle is also within a 90-degree angle because this line is horizontal and this line is vertical. So if we subtract 45 degrees, we get 45 degrees here. So if you look at the original closed triangle of vectors, we're going to have a triangle that looks like this. It's going to go straight down. It's going to be 45 degrees down here. Then we're going to have a vector going up and then another vector going up from there. This is going to be 30 degrees here because it's matching with that. And then finally that 60 and that 45 will add up to be 105 degrees. And we'll know that this side length right here, the magnitude of that vector is 196.2 newtons. And we're going to be perfectly set up now to determine the magnitude of these other 2 vectors, which is what the question's asking. So this is one way of going about it. So let's do it a little more neatly. We're going to insert angles. I'm now repeating everything in a little neater fashion from the left-hand diagram to the corresponding spot in the right-hand diagram. That 60-degree angle goes there. That 45-degree angle goes there. That 45-degree angle goes there. And when you do all that, we add the 60 and the 45. That becomes 105. Just to show you again, we're adding that 60 and 45 right there. It becomes 105. Now the green 45 is part of a 90-degree angle. We're saying this is 90 degrees because that's a horizontal and that's a vertical. So because of that, we're going to end up with 45 right here. And since you've got a 45 and a 105, that's 150. So within the triangle itself, we'll need another 30 up here. And so that's a 30. The way I described it earlier was I brought this 60 over and then subtracted the 90 minus 60 to get the 30 that way. So there's different ways of thinking about this. But however we do it, we end up with that closed triangle on the right. And now we're set up where we can use our sine law if we want. And just to repeat a concept I mentioned earlier, we don't have to worry about ambiguity in using the sine law here. And the reason we don't have to worry about ambiguity is we already know the biggest angle. So there's no possibility of obtuseness. So we can find each of these angles. Sorry, we can find, oh, sorry, I'm speaking out of turn. We don't have to worry about ambiguity because we're not finding an angle, we're finding a side. So strike that last 30 seconds. We're using the sine law to find a side, so there's no reason to consider ambiguity at all. There's never ambiguity when you use the sine law to figure out the magnitude of a side. So anyways, we get here T1, the magnitude of T1 using that sine law will be 143.6, and the magnitude of T2 using that sine law will be roughly 101.6 newtons. And so therefore the tensions in the ropes magnitude-wise will be roughly 143.6 newtons and 101.6 newtons. We've answered the question. Now, what's method 2? Method 2 is if we break it up into components. So we'll use that component method. We know the net horizontal force of the two tensions has to be 0 because there's no horizontal movement. See, the gravitational force is a pure vertical force. So that means that we know for sure it's not providing any horizontal movement. Well, since the package itself has no horizontal movement, we know that these two forces that create the only possible horizontal movement must be canceling each other out in a horizontal fashion. So that's what that paragraph says there. We know the net horizontal force of the two tension forces is 0 because the gravitational force is providing 0 net horizontal force, and there's 0 net horizontal force overall. So now let's go back to components. If we think in terms of components, what we're going to do is we're going to evaluate that horizontal vector and that horizontal vector. So the first one, that first horizontal vector that I mentioned a minute ago, that will be the magnitude of T1 times the cos of 60. And this second one, that'll be the magnitude of T2 cos 45. So those two must be equal to each other. Now, one's going one way and one's going the other way. And so the magnitude of the T1 horizontal force equals the magnitude of the T2 horizontal force. So we're not going to put any negative signs here. We're saying that this movement to the left equals this movement to the right. So we're saying these magnitudes equal each other. Okay? So in other words, now the cos of 60 is 1/2 and the cos of 45 is √2/2. So we're ultimately saying that the magnitude of T1 is √t/2 times the magnitude of T2 divided by 1/2. That's another way of saying 2√2/2 times the magnitude of T2. Or in other words, that's another way of saying √t to T2. So just doing some pretty straightforward simplifying here, we see that the magnitude of T1 is equal to √2 times the magnitude of T2. Now, that's one equation with two unknowns. We're going to need a second equation. And the way we're going to get the second equation is to recognize that the net vertical force of the tensions has to be roughly 196.2 to counteract the force due to gravity. See, this, if left to its own devices, that gravitational force is going to make that package move down. But we know the package isn't moving. So since the package isn't moving, that means these vertical force, the vertical components of these forces must be adding together to totally counteract that. So the vertical component of T2 plus the vertical component of T1 must perfectly equal the vertical component of the gravitational force due to gravity, which is the entire thing. therefore counteracting each other, because the T1 and the T2 forces are moving in an upward direction. The other one, force due to gravity, is moving downward. So they're going to have to cancel out. So what we're saying is the vertical component of T1 plus the vertical component of T2 must equal roughly 196.2 newtons. So what is the vertical component of T1? Well, the vertical component of T1 is this vertical line that I'm drawing right there, that I'm pointing at. Well, that vertical line is roughly equal to the magnitude of T1 times the sine of 60. And the vertical component of T2, there's T2 drawn. Well, the vertical component of T2 is that horizontal line that I'm pointing at here. That vertical line that I'm pointing at here, and that vertical line has a magnitude of the T2's magnitude times the sine of 45 degrees. So adding those two vertical components together, we're going to roughly get 196.2 newtons. Well, the sine of 60 is root 3 over 2, and the sine of 45 is root 2 over 2. Adding those together, we get that equation as you see it there. Now, we learned in the previous, doing the horizontal components, we learned that the magnitude of T1 is roughly equal to root 2 times the magnitude of T2. So why don't we just sub that straight in for T1? So we've got T1 right here. Instead of T1, we're going to call it root 2 T2. When we do that, we get this equation. And there's only one unknown there. The only unknown is magnitude of T2. So we do a little bit of collecting. First, we do a little bit of simplifying. Root 2 times root 3 over 2 is root 6 over 2. We do that. Now we're going to factor out the magnitude of T over 2. So from that line right there, we're going to factor out the magnitude of root T over 2. We're going to factor out the magnitude of T2. When we do that, we've got a coefficient of root 6 over 2 adding a coefficient of root 2 over 2 right there. And when we add root 6 over 2 plus root 2 over 2, we get root 6 plus root 2 over 2. So this right here, the magnitude of T2 times root 6 plus root 2 all over 2 is roughly equal to 196.2. There we can just simply divide and figure it out. And when we do that, we can multiply, numerator and denominator both by 2. And we end up with this as our answer for the magnitude of T2. And when we then realize, well, T1, go back and sub in like we learned in grade 10, the magnitude of T1 will just be root 2 times T2. We get this as our answer for the magnitude of T1. Now, in the previous example, we used decimal approximations, and so we can do that here. This first one is roughly equal to 101.6, right there. That's roughly 101.6. And the second one is roughly equal to 143.6, right there. And so we get the same answer either way.